In the last lecture, we have discussed about the Biot-Savart's law. Also, we have seen how to calculate the magnetic field intensity using the Biot-Savart's law. Now, in this lecture, we are going to discuss about the Ampere's circuit law, and using the Ampere circuit law, how to calculate the magnetic field intensity. So, let us start our today's discussion, that is Ampere's circuit law. So, Ampere circuit's law states that the line integral of H, that is the magnetic field intensity, around a closed path is same as the net current IENC. Here IENC means the current enclosed, enclosed by the path. So, in other words, that is, we can say the circulation of H equals to I enclosed. Now, the mathematical form of the Ampere circuited law is represented by 21.1, which says that the closed line integral H dot di equals to I enclosed. And this Ampere circuit law is similar to the Gauss law, because Ampere's law is easily applicable, or it can be easily applied to determine H, that is the magnetic field intensity, when current distribution is symmetric. So, the Ampere circuit law can be applicable only if we consider the current distribution is symmetric. Now, we are going to use this equation 20.1 to calculate the magnetic field intensity H only when the symmetrical current distribution exists. As I said, the Ampere's law is the special case of Biot-Savart's law. So, this Ampere circuit law can also be derived from the Biot-Savart's law. Now, we are going to apply the Stokes theorem to the left hand side of this equation 21.1. If we apply the Stokes theorem, and we know using the Stokes theorem we can relate the line integral to the surface integral. So, here I enclosed will be equals to the line integral, closed line integral H dot di, which is equals to surface integral of, open surface integral of del cross H dot ds. But we know I, that is the current enclosed by the Amperian path, that Amperian path we will see afterwards. The current enclosed I, which can be written as surface integral of J dot ds, because I is the current that can be calculated using the surface integral of current. J is the current density J dot ds. Now, if by comparing the expression 2 and expression 3, we will get, you see here that the surface integral of del cross H dot ds, which is equals to the surface integral of J dot ds. So, if the integrands of left hand side and right hand side of this equation 4, then we can get the expression del cross H equals to J. Here expression 5 is representing the Maxwell's equation. Now, this expression del cross H equals to J is the third Maxwell's equation, and equation 20.1 is showing, this equation 20.1 is the integral form of the Ampere circuited law or Maxwell's equation, and equation 5 is the differential form of the Ampere's law. And also we can see from this expression 5 that del cross H equals to J. That means that del cross H is not equals to 0. Now, the meaning of this, that del cross H is not equals to 0, is that the magnetic field is not conservative in nature. Now, we are going to see some applications of Ampere's law. So, before going to apply the Ampere's law, we need to know that Ampere's law can be used to calculate the magnetic field intensity H provided the current distribution is symmetric. The current distribution is considered symmetric, just like we did in the case or for the case of Gauss law. And here we will consider an infinite line current, an infinite current sheet, and an infinitely long coaxial transmission line. For all these three cases, we are going to find out the magnetic field intensity using Ampere's law. So, for each of the above cases, that means the infinite line current, infinite current sheet, infinitely long coaxial transmission lines, we will apply that line integral of h dot di equals to I enclosed. So, the first case here we are going to consider the infinite line current. Before that, the point here it is written, for symmetrical current distribution di is either parallel or perpendicular to h. Now, the first point we are going to discuss about the infinite line current. For the infinite line current, what will be the magnetic field intensity? Now, for that you can see the diagram here. In this diagram, we have considered that the infinitely long filamentary current carrying conductor is placed along the z axis, and through this conductor the current I is flowing. Now we want to find out the magnetic field intensity at the observation point P here. To find out the magnetic field intensity at this point P, we need to draw a closed path in which the P is present. So here you can see that we allow a closed path to pass through P. This path, this imaginary path on which the Ampere's law is going to be applied is known as the Amperian path. Just like we have seen in the case of electrostatic, the Gaussian surface, here in this case in the magnetostatic we will consider the imaginary line that is called the Amperian path. So for the line current we have drawn the circular Amperian path, because that uh, Amperian path is defined or is intuitively drawn because we know, we have the idea that H equals to I by 2 pi r Fi for the infinitely long current carrying conductor. So if this happens, then H will be constant if R is constant, because I is constant, 2 pi is constant. So if R is constant, then H will be constant. So keeping in this mind, we can say, or we can intuitively draw the Amperian path, that is the circular path which is encircling the current carrying conductor. Now we are going to use the Ampere's law, because this path encloses the whole current I. So according to the Ampere's law, I enclosed equals to line integral of H dot dl. Now you see that I enclosed means the current enclosed by this Amperian path. So here I is the current flowing through that. So I enclosed will be I, and here you can see that the line integral of H dot dl. H is a vector, so H can be represented as H phi Fi. So this vector, so this vector H has the magnitude H phi we are considering, and it is directed along the direction Fi. Dot dl. To find out dl, here you can see that a dl length we have considered, and in this dl length the current element we can consider, that is the di, but dl length we can find out if we draw the line here from this origin to this point dl, that will be the radius. So the variation of the radius and the angle of variation will be d phi. So d phi into r will give us the length dl. So that is why r d phi a phi. Now Fi dot Fi equals to 1. So what we will get here from that H phi, that is the constant, integration of R d phi. So R is also is constant. So d phi, if we take the integration 0 to 2 pi, we will get 2 pi into R. So I is equals to H phi 2 pi R. Now H phi will be equals to I divided by 2 pi R, and we know that H is a vector and H equals to H phi Fi. So if we put the magnitude of H here in this expression, we will get I by 2 pi r a phi as expected, because we have seen in the using the Biot-Savart's law for the infinitely long current carrying conductor, the magnetic field intensity H equals to I by 2 pi r into a phi. But here you can see that how easily we have calculated the magnetic field intensity H, but the condition is that the current distribution is considered symmetric. Now the second case we are going to consider, that infinite sheet of current. So for that we have considered the x, y, z coordinate system, and in this coordinate system the infinite current sheet is placed on the xy plane, or we can say it is placed in z equals to 0 plane. And also we have considered this, that the current density is uniform and which is moving along the y direction, and the current density is k. So as the current density k is a vector, so this k can be represented as ky ay, because it is moving along the direction of y. That is why k is a vector, so its magnitude is considered as the y component of k, so ky, and it is moving along the y direction, so unit vector is ay and its unit is ampere per meter. Now we are going to apply the Ampere's law to the Amperian path. Here in this case, the Amperian path should be rectangular path. Here you can see that I have drawn a rectangular path which is cutting this infinite sheet, and we will move from 1 to 2, 2 to 3, 3 to 4, 4 to A, and 2 to 3 distance is B, and A to 1 to 2 is the length is A. So before going to apply the Amperian path, that is the rectangular closed path 1 2 3 4 1, we know that the using the Ampere's law we can write the line integral of H dot dl equals to I enclosed. Now here we have to calculate first the I enclosed. I enclosed means the current enclosed by the Amperian path. So here the Amperian path is 1 2 3 4 1. So here the current density is K and this distance is B. So the total current enclosed by the Amperian path can be written as K into B, that is Ky magnitude into the length B. Now to evaluate the integral, we first need to have an idea of what H is like. So that means we need to know the nature of the H for this infinite sheet of current. So here we have considered that to achieve this, we consider the infinite sheet as comprising of the filaments. That means the infinite sheet is divided into pieces, small lines, If we divide this, then we will get the n number of strips from this infinite sheet of current. And if we rotate this diagram so that the y axis is along the direction, that means it is coming out of the page, then we will get here the one point, we will get here one strip, we will get, and this strip is given here at point 1. This is the first strip and this is the last strip, that means in this direction this is the last strip. So now if we consider this is the strip and current is coming out of the page, then encircling this other fingers encircling this current carrying conductor will be the direction of the magnetic field intensity. So we need to draw a circle here. If we draw a circle here at this particular point which is above the sheet can be drawn, that is the magnetic field intensity can be drawn, which is tangential of this point, so dH1. Similarly for this filamentary current carrying conductor also the magnetic field will rotate along the circular path. So here also the circular path will represent the magnetic field intensity. So at this point the magnetic field intensity will be tangential at this point. So that is represented as dh2. Now the equivalent, uh, uh, the, uh, if we want to find out the resultant of dh1 and dh2, we will see that the dh at this point, that is above the sheet, will be along the direction of x, because it is the x direction, it is the minus x direction, y is coming out. So in the x direction we have one magnetic field intensity. Similarly, if we want to find out, if we see below the sheet, then also we will get the magnetic field, the resultant of magnetic field intensity. That is the same way we can calculate, that is dh, and it is moving along the minus x direction, and that is written here as evident in the figure. The resultant dh has only an x component. So from this diagram we can understand that the magnetic field intensity has only the x components, y component and the z component will be 0. Also, h on one side of the sheet is negative of that on the other side. So above the sheet it is positive, below the sheet it is negative, because it is moving along the minus x direction. Now, considering the infinite sheet, the sheet can be regarded as the consisting of such filamentary pairs, so that the characteristics of each of for a pair are the same for the infinite current sheet. So as we have considered the first strip and the last strip, for that we got the expression of the dh, which is uh, moving along the x direction, either it is positive x or minus negative x. So for all the other strips also we will get the same direction of the magnetic field, that is the x direction. So the h, vector h, can be represented as h naught ax when z is greater than 0, that means above the sheet, and minus h naught ax if the z is less than 0, that means below the current sheet. Here the direction we got, but this h naught is not yet determined. So now our aim is to find out this magnitude of h. The direction of h we got. Now the magnitude of h we are going to find out. To find out the magnitude of h, we need to calculate the h dot dl. So evaluating the line integral of h in equation 21.8 here, along the closed path given in the last slide, that means along the path here, this is the path. Along this path, if we calculate h dot dl, then we can calculate that here. First we will calculate the h along the path 1 to 2, then we will calculate h along the path 2 to 3, then 3 to 4, 4 to 1. So here you see that for the first case it is 0 to 1, 1 to 2. If we consider the integration, then the component of h will be 0, and here you see that 1 to 2 we are moving. So along 1 to 2 there is no component of h field, because we know the h field has only x component. So in the z that is there is no z component, so this will be equals to 0. So this is 0 into minus a, because we are moving from 1 to 2, that is positive to negative, that is minus a, plus we are moving now 2 to 3. So here 2 to 3 we are moving. So for this case we will have the expression, that is minus h naught, because you know h naught is positive along the plus x direction, negative in minus x direction. So it is minus h naught into minus b, because we are moving along the minus x direction. So 2 to 3 is the minus x direction, that is why minus b, plus again 3 to 4 in the opposite in the other side. Here 3 to 4 we are moving positive z direction, so a will be positive but h will be equals to 0. Similarly, the 4 to a we have b, the length, that is dl, into h naught. It is positive because it is moving along the plus x direction. So by solving this we will get that twice of h naught b. So here you see that line integral of h dot dl we got twice of h naught b, but Also we got h dot dl equals to I enclosed, that is equals to kyb. So by comparing this equation 7 and equation 9, we got the expression h naught equals to half into ky. So you can see that earlier we got the direction of the magnetic field. Now we got the magnitude of the the H magnetic field intensity. So finally we can write this H equals to half of kyax for z greater than 0, that is above the sheet, and minus half kyax below the z, that is z minus at z less than 0. But this is the expression we got for the case when the current is flowing in the y direction, and we got the expression for above the sheet, below the sheet. For in general, for infinite sheet of current density k in ampere per meter, in general the H is represented as half into k. Here not ki, the component here ki we have considered to calculate, but k, the current density or the current flow, can be in any direction, either x, y, z. So that is why half k cross an. Cross an means here an is a unit normal vector directed from the current sheet to the point of our interest. So if it is below, then it will be negative. If it is above the sheet, it will be positive. So for that we will get the expression. So in this way we can calculate the magnetic field intensity for infinite sheet of current. Now the third case we are going to discuss, that is infinitely long coaxial transmission line. So here first we are going to consider the cross-sectional view of the coaxial transmission line, and this infinitely long transmission line consisting of two concentric cylinder having their axis along the z-axis. So both the axis of the inner cylinder and the upper cylinder having the axis along the z direction, and this is the cross sectional view. And the radius of the inner conductor is a, and it is carrying the current I, and the current is coming out. While the outer conductor, this is the outer conductor, blue line, this is a strip, circular strip. The outer conductor has the inner radius b, the inner radius is b, and thickness of this conductor is t, and carries the return current minus I. So current moving in the into the page, and it is the direction will be in the opposite direction of that of the current. Now we want to determine the magnetic field intensity anywhere, either it is at the center or outside the transmission line. Anywhere we want to find out the magnetic field intensity. For that we will consider the current distribution is symmetric, and we are going to apply the Ampere's law along the Amperian path. Here we have considered 4 Amperian path. So we are going to discuss about the 4 conditions or 4 possible regions, that is R, that is the radius will be in between 0 to a. So if the radius of this Amperian path varies from 0 to a, what will be the magnetic field intensity? If this radius varies, that is radius of the Amperian path varies, its limit, or it varies from a to b, what will the magnetic field intensity? Or if it varies from b to b plus t for this strip, so we need to find out also the magnetic field intensity for this case 3 also. And the last one is R greater than equals to b plus t. So for the region 0 less than equals to R less than equals to a, for the first case we are going to apply the Ampere's law to the Amperian path L1. So this is the L1 path, we have Amperian path we have considered. For that we are going to apply the Ampere's circuit law. Here the line integral of h dot dl equals to I enclosed. So I enclosed means the current enclosed by the Amperian path, that is equals to j dot ds we know. Now this j we need to find out, and this ds we need to find out. Here you see that the current is uniformly distributed over the cross section, therefore j can be written as the current density. Current density means the current divided by the area. So here the current current is coming out is I, and the area we can find out pi a square, because A is the radius of this conductor. So the area, total area is pi a square, and I by pi a square will give us the current density which is flowing through the inner conductor, and it is obviously moving along the z direction, that is why Az. Now we need to find out ds. Ds is the unit area. So unit area, if we want to find out in this cross sectional area, so in this direction it is r d phi, and in this direction it is dr. If you have studied my previous lectures of cylindrical coordinate system, you will understand how to consider the ds area in this circular area. So from that also you can consider. So here ds equals to r d phi into dr az. So now if we put the value of j and ds in this expression, we can calculate I enclosed, that is equals to integration of j dot ds. So here I by pi a square is constant, so it is taken outside. Now surface integral, and its limit is phi is limit of phi is phi is 0 to 2 pi, and limit of r is 0 to r. So r dr d phi. So now if you solve this expression, you will get the expression I r square by a square. This is the simple expression here. Integration of phi to 0 to 2 pi d phi, integration of 0 to r dr. From that you will get this expression. Hence the equation 12 becomes, you see that I enclosed we got. Now h dot dl can be represented as h phi d phi dot, here we have discussed earlier. Here in this case you can see that from that we will get the expression h phi 2 pi r. So that expression h dot dl will give us h phi 2 pi r, which is equals to the I enclosed, that is equals to I r square by a square. So from that we will get the h phi equals to I r by 2 pi a square. So this is the case, or the magnetic field intensity, magnitude of the magnetic field intensity for the case 1, where the region we have considered is 0 less than equals to r less than equals to a. Now for the case, second case, that is a less than equals to r less than equals to b, we have used, or we are going to use the Amperian path L2. Here you see that this is the L2 path we are going to use, and we are going to use the Ampere Circuited Law. So here Ampere's law again is h dot dl, line integral of h dot dl equals to I enclosed. Now if we consider this is the Amperian path, so the total current enclosed by this Amperian path L2 is I, so that is why I enclosed equals to I, and h dot dl, from that again same way we can find out h phi 2 pi r. So ultimately h phi we will get I by 2 pi r, since the whole current I is enclosed by L2. Now the third case we are moving, that is the Amperian path we are considering inside the strip of this outer cylinder. So here L3 path we have considered. So the current flowing through this Amperian path, current enclosed by this Amperian path, we need to calculate. After that we need to apply the Ampere's law. So for that, first we need to calculate the current flowing through this strip, so the inner strip. After that we will add that current and the current flowing through the inner conductor. So for that, here the calculation I have used. Here you see that this is the third case. For that we have considered the path L3, here L3, and we know the Ampere circuit law, that is h dot dl equals to I enclosed, and we know h phi equals to 2 pi r. So now our aim is to find out I enclosed, that is the critical part of this calculation. H dot dl can be calculated for all the cases, it is h phi 2 pi r, but to calculate the I enclosed by the Amperian path is the critical part of this topic. So here I enclosed, that means I enclosed equals to I, that is the current flowing through the inner conductor, plus J dot ds. This J dot ds is the current moving into, that is the current flowing through this strip. This strip we need to calculate the current going into the page through this strip. We need to calculate. This calculation is given here. First we need to calculate J, then ds. So J is the current density. That current density can be calculated as I by the area of this conductor. So J equals to minus I, because current is moving in the opposite direction for the outer conductor, so it is minus. Again you can see that here the current I is moving into the page, and in the for the case of the inner conductor it is coming out, so I is equals to minus I. So minus I divided by the area we need to consider, so pi into b plus t square minus b square. So here b, here b plus t square, this is the total length, b plus t square minus b square. So here from that we will get the expression, that is the strip area pi a square, just like the pi a square. So here pi b plus t square minus b square. So from that into along the z. Now I enclosed, we will get the I plus j dot ds. Here j we got this expression, the same expression, and ds you know the same expression, that is integration of phi equals to 0 to 2 pi r equals to b to t, that is the strip. For that we are calculating, so r dr d phi. So by solving this expression we got the expression I enclosed, that is that I equals to 1 minus r square minus b square by t square plus 2 bt. This is a simple calculation. If you understand how to calculate this I enclosed, then all the other calculations will be easier. So as we got the I enclosed, we got h dot dl, so we can find out h phi. So this expression 21.16 is representing the magnitude of h for the case 3. Now for the case 4 is the most simplest case. For the case 4, that is r is greater than equals to b plus t, we are going to use L4. So here L4, if we are going to use L4, you see that L4 is the Amperian path which is outside the transmission line. So now here h dot dl equals to I enclosed. So I enclosed is I minus I, because I enclosed by the Amperian path L4 will be equals to 0, because total current coming out of the inner core will be the same current which is moving into from the outer core. So the total current will be 0. So h phi will be equals to 0. Now if we want to sum up the what will be the magnitude of h for the transmission line, coaxial transmission line, this is the h phi expression. For the case 1 it is ir by 2 pi square a phi. For case 2 it is I by 2 pi r a phi. For case 3 you can see that, and for case 4 it is 0. Also we can sketch the magnetic field intensity of the coaxial transmission line. If the r varies, what will be the variation of the magnitude of h, here h phi. So you can see that from 0 to a, if the radius increases from 0 to a, the magnetic field intensity, the magnitude of the magnetic field intensity increases linearly. From this expression you can see that because this expression you can see that I is constant, 2 pi is constant, a is also constant, so r varies, h phi varies r proportionally, so it is linearly increasing. Now for the second case from a to b, you can see that h varies as 1 by r, so it will decrease up to b, and its value will be I by 2 pi b. And for the case when r reaches to a, the current will the magnetic field intensity will be I by 2 pi a, because r will be a square cancel out, so I by 2 pi a. And for the third case, here r will decrease also. Obviously it will decrease. From this uh, expression we can understand it will decrease, and it will be 0 after b plus t. So that is all about the Ampere circuited law or Ampere's circuit law and its application to calculate the magnetic field intensity provided the current distribution is symmetric in nature. Also, we have seen how easily we can calculate the magnetic field intensity if we consider the current distribution is symmetric. So that is all for today's class, students. If you have any queries, you can put it in the comment box. Thank you very much.